Thank you for the introduction. So as Maria said, the question I want to answer is, are we headed for a BBR-dominant internet? So we just saw from Simon's talk that BBR can be unfair to cubic flows, and if you care about throughput, then it makes sense to switch to BBR. So the question I'm trying to answer is, okay, so since everyone cares about throughput on the internet, is everyone going to switch to BBR? So since BBR was first introduced in 2016, it actually came with the promise of higher bandwidths. And this was partially because early adopters like Google, Spotify, and Dropbox, they actually reported higher throughput and lower delay jitter by switching to BBR from algorithms like Cubic. And it's also easy to find blog articles and posts on tech forums that recommend switching to BBR to get higher throughput. And unsurprisingly, this performance benefit has not gone unnoticed. So in a measurement study that we did in late 2019, we basically probed some 20,000 odd websites to figure out what congestion control algorithm they were running. And what our results showed was that even though Cubic was still dominant, BBR was quickly catching up. So BBR was introduced in 2016, but 3 short years since it was introduced, it was already controlling 18% of the websites that we tested. And because most of these websites actually stream video, it actually has a disproportionate share in the downstream bandwidth. In fact, it contributes close to 40%. So the question we want to answer is that, obviously, given the rapid adoption and the performance benefits, if you care about throughput, you're going to consider switching to BBR. So the natural question then to ask is everyone going to switch to BBR at some point? So while trying to answer this question, we realized there are 2 sub-problems that we need to deal with. The first is we need to sort of understand how BBR's throughput benefits are going to evolve as more and more people on the internet start using BBR. Are they going to stay the same? Are they going to improve? Are they going to go up? How's that going to play out? So for this, we actually propose a simple mathematical model. So we only look at steady state, so I didn't have to work as hard as Simon did. But so we only look at the steady state throughputs, and then we try to predict how they're going to change as more flows at the bottleneck switch to BBR. And the second question we need to answer is, given that this is how the throughput benefits are going to evolve, how is that going to play out in the final congestion control makeup of the internet? For this, we'll be using standard game theoretic analysis, and we'll be extending our model to sort of predict where the Nash equilibrium distribution of cubic and BBR flows lies on the internet. So before I get into the simple model itself, it's probably handy to remind everyone about how our 2 algorithms of interest work, namely Cubic and BBR. So Cubic is a congestion control algorithm, as you all know and would have studied in undergrad. It probes for more and more bandwidth by increasing its congestion window size, and it only backs off when it sees a packet loss. When it does see a packet loss, it treats this as a signal of congestion, and it backs off by reducing its congestion window size by 30%. And for this reason, Cubic is lovingly called a buffer filler, because it likes to fill the buffer till it sees a packet loss. So basically, Cubic is going to continue probing for more bandwidth till that shows up as a buffer overflow and a packet loss, and only then it's going to back off. So what about BBR? BBR actually opts for not using packet loss as a congestion signal because it does not want to bloat the buffer. Instead of that, BBR is actually a rate-based algorithm that uses RTT and bandwidth estimates to infer congestion, as Simon just covered. But what's interesting with BBR is that there have been previous works that have found that even though BBR is rate-based, its performance in steady state can actually be limited by what BBR's congestion window is. So looking at BBR's congestion window is still very interesting. And it turns out this congestion window is actually quite sensitive to BBR's RTT and bandwidth estimates, since it's equal to twice the BDP. Another interesting mechanism associated with BBR that I think Simon did not go through in detail was that to measure the minimum RTT, BBR actually tries to collaboratively empty the bottleneck buffer so that it sees empty buffer, and then it can measure the minimum RTT. So even though in the steady state, BBR will maintain some fixed number of packets in the buffer, every 10 seconds it will empty this buffer to see an empty path, measure the minimum RTT, and then resume in the normal mode of operation. So here's where the problem actually lies when BBR and cubic flows compete, at least in the steady state, because I just went over how BBR would like to empty the bottleneck buffer every 10 seconds. But we know cubic is a buffer filler, so what's going to happen is that when BBR tries to empty the bottleneck buffer, it's not really going to be empty, because you're still going to have some residual cubic packets. And that's what causes the problem in BBR, which we call as RTT min overestimation. So when BBR flows think that they have actually emptied the bottleneck buffer, it's actually not empty, there are still some extra packets over there, and BBR ends up overestimating the minimum RTT. This ends up in causing BBR to be more aggressive and then eventually unfair to cubic in certain buffer sizes. So because we have a very simple model, it turns out that it's enough to just model this interaction to predict what throughput shares BBR and cubic flows will get when they interact with each other at a common bottleneck. So to go over it step by step, I'll probably go over the assumptions that we use for all of our modeling in the paper so that later on we can look at the results in context. So the first assumption we make is that we assume that all the flows have the same RTT. Now, honestly, we did this for the sake of simplicity, but we don't think it's too far-fetched since most of your traffic is being delivered by CDNs. That said, it's still a weak assumption because not all CDNs are built same, and still you're going to have some amount of RTT diversity. So later on in the presentation, I'll go over what happens to our predictions when you remove this assumption. The next assumption we make is the buffer size is at least 1 BDP in size. So this is an assumption we make in the model, but empirically we still evaluate lower buffer sizes. And the reason we do this is so that we can make sure that the link is always fully utilized. We also assume that BBR has 2 BDP packets in flight, which is based on a previous result. We assume that the packets are uniformly distributed, the buffer is drop tail, and BBR's reduction in bandwidth while trying to measure the minimum RTT is negligible. So based on these simple interactions and our simple assumptions, we're able to build a very simple pipe model where we're really interested in only 3 equations. So the first thing we look at is BBR's throughput. And as Simon said, we can just calculate it by packets in flight divided by the amount of time it took to deliver this flight of packets. So that's your C-wind divided by your end-to-end delay. Then because of the RTT overestimation problem, we also need to model the amount of RTT overestimation, which we do by calculating the minimum RTT plus the delay caused by the residual cubic packets. Finally, we need to estimate what the amount of residual cubic packets is going to be. So for that, we very simply model cubic's back-off behavior. Okay, so we have our 3 simple equations. What we can do is we can take these equations, we can apply our assumptions as constraints to these equations and solve these set of linear equations to get our bandwidth shares. And when we do that, it turns out that for cubic, we can actually get a nice closed-form solution where you get the throughput as a function of the RTT, the link capacity, and the buffer size. And because we know that the link is completely utilized, we can simply subtract this from the link capacity to get cubic's bandwidth share. So let's try to validate this simple basic 2-flow model, and then we'll move on to multiple flows. So for validating the simple 2-flow model, we hooked up 2 physical machines, and then we launched 1 cubic and 1 BBR flows and made them compete in a variety of network conditions. We pumped these numbers through our model as well as made empirical measurements, and then we compared them both over a range of buffer sizes. So we see that over a large range of buffer sizes, our model, which is admittedly very simple, can actually predict the throughput shares reasonably well. So how do we actually extend this model to multiple flows? Because we know the internet has more than 2 flows, so we need to definitely do better, right? So it turns out that for multiple flows, there's actually just one equation that causes a problem, and that's the equation which we use to calculate cubic's residual packets. So recall that for calculating cubic's residual packets, we just use cubic's back-off fraction. But when you have multiple cubic flows, you're not always guaranteed to have 70% of the packets in flight during a back-off. The reason this happens is because when you have multiple cubic flows, they might be backing off at different times, and that causes a different number of packets in flight. So if all your cubic flows back off together, they're going to drain the buffer a lot more than if your flows back off one at a time. So to solve this problem, we actually get rid of our single prediction and we start predicting bounds based on the best case and worst case scenario of these synchronizations. So we have a sync bound, which is based on the assumption that all the flows are perfectly synchronized. And when all the flows are not perfectly synchronized, we have a desync bound. And then we assume that all the real results that we're going to get are going to operate between these two bounds. Okay, so we have augmented our two-flow model to a multi-flow model. So let's get back to validating. So to validate this model, what we did was we launched, in this experiment, we launched 5 cubic and 5 BBR flows through a 100 Mbps bottleneck with 40 ms RTT. And then we plotted the average per flow bandwidth of BBR flows and compared it with the region that our model predicts. So the first thing that we see is that the model does a reasonably good job again in predicting the throughput shares, and actually the empirically observed throughput is always within our predicted bounds. But okay, we've done a lot of math, so let's take a step back. Why did we actually do all of this math? Well, the reason we wanted to look into this is because we wanted to answer the question that how are BBR's throughput gains going to evolve as more flows start adopting BBR. So let's do exactly that. So in order to model such a network, what we did was we launched 20 flows through a common bottleneck, and all of these 20 flows were cubic flows to start with. And then across trials, we slowly started switching flows from cubic to BBR, and then saw how BBR competed against the rest of the traffic. So over here, I'm plotting the average bandwidth of the BBR flows across different shares of BBR and cubic at the bottleneck. And in this case, we're looking at 3 BDP, but we have done this experiment over a variety of buffer sizes. So what we see immediately across all of our experiments is one key trend, which is that as the number of BBR flows at the bottleneck increases, BBR's throughput actually exponentially decreases. So this is BBR's per flow throughput, and it exponentially decreases. So this is actually quite interesting because this means that as more and more people start adopting BBR on the internet, the throughput benefits over cubic are going to go down. And the other interesting question to ask over here is this. Now that we know that BBR's throughput is going to go down, is there a point at which it's going to go down below cubic and cubic's going to become competitive again? So how low is too low? So for this, let's define a new thing called the Nash equilibrium distribution of cubic and BBR flows. So if you're familiar with game theory, what we basically consider is that in a given network, a distribution of cubic and BBR flows is considered to be the Nash equilibrium if none of the flows can get throughput benefits by switching algorithms. So basically that becomes the steady state in this game where no one wants to switch algorithms, and that's how the network's going to remain. Now this is interesting from the internet standpoint because if everyone's going to make the performance-based decision to switch to BBR, then this distribution is most likely what the internet will head towards. So now that we have this new quantity defined, let's revisit the trend that we saw earlier and recontextualize based on our definition of Nash equilibrium. So again, over here in the y-axis, I have BBR's per flow bandwidth. On the x-axis, I have arranged all the possible distributions in increasing order of number of BBR flows. And then if you plot BBR's average bandwidth, you sort of get this exponentially decaying curve. As a reference, I've plotted the fair share bandwidth of the BBR flow as this dotted line. So in this graph, let's actually evaluate one of the distributions, which lies at the intersection of the red line and the fair share line. So this distribution is actually the distribution at which all your BBR flows are getting the fair share. And this distribution is particularly interesting for a couple of reasons. So if you shift to the left in this distribution, you actually, what shifting to the left means is that a BBR flow is switching to cubic. So when you switch to the left, you end up in a region where BBR does better. But if you move to a distribution on the right, you move into a region where cubic is doing better. So you basically have this dichotomy that's defined at this distribution where all the flows are getting the fair share. So now that we know that this is a particularly interesting distribution, let's try to understand what happens when flows try to switch algorithms over here. So if we have a cubic flow that tries to switch to BBR, the number of BBR flows in the network is going to increase and your state is going to move towards the right. Now what moving towards the right means is that you're moving into a region where cubic is doing better. So the switching flow does worse. Similarly, if you have a BBR flow that's switching to cubic, now the switching flow is moving into a region where BBR does better. So again, the switching flow does not have the incentive to switch algorithms. And this is actually quite perfect because this is exactly the distribution that we're looking for. We're looking for a stable distribution where none of the flows have the incentive to switch from cubic to BBR. Therefore, this must be the Nash equilibrium. So to verify our predictions of the model, we basically used this analysis, extended our multi-flow model, and then tried to figure out what the predicted region looks like. Empirically, we launched about 50 flows through a 50 Mbps bottleneck, and then we tested all combinations of cubic and BBR flows and figured out what the Nash equilibrium is going to be. So the first trend that we see, again, is that our model does a good job in predicting where the Nash equilibrium is supposed to lie. But the more interesting trend over here is that majority of your Nash equilibrium distributions actually have a mix of both cubic and BBR flows, which means that your Nash equilibrium actually lies in a state where you have both cubic and BBR flows, or basically that BBR is not a dominant strategy for the future. So in the context of internet, it basically means that even though BBR is really hot right now, cubic is here to stay. Because once enough people start running BBR, cubic is going to become competitive again. Well, all that is true unless your buffer sizes are really small, because if your buffer size is below 1 BDP, we have found that BBR is actually the clear dominant strategy. And if the entire internet is running really tiny buffers, then yes, we are going to move towards an all BBR internet. Now, as I mentioned earlier, one of the assumptions that we made was all the RTTs are similar, but this is a weak assumption that we want to test against and see what happens to our predictions once we remove this assumption. So to do so, we actually launched experiments where we have a whole group of flows that have RTTs from different RTT buckets, and again, we launched all combinations, and we try to compute where the Nash equilibrium lies. So the first thing that we see is the fact that there is a Nash equilibrium, so that's a good thing. So even in mixed RTT scenarios, you're going to get a Nash equilibrium. And more importantly, this Nash equilibrium is also going to lie at a mixed distribution. So even in mixed RTT settings, cubic is going to survive. The more interesting trend that we see here is that the Nash equilibrium distribution, in the Nash equilibrium distribution, the shorter RTT flows always tend to go for cubic, and the longer RTT flows always tend to go for BBR. So in the paper, we discuss how we think that this is down to how RTT fairness works in cubic and BBR. Finally, as Simon mentioned, Google's also working on BBR v2, so that's another thing that we wanted to test against. We redid our experiments by replacing BBR with BBR v2, and again, we found mixed Nash equilibriums. Just as a comparison, we also plotted our predicted region, and we saw that our predicted region sort of underestimates the number of cubic flows at the Nash. And the reason this happens is that overall BBR v2 is a little less aggressive, so cubic can actually claim more flows at the Nash equilibrium. In summary, what we show is that we present a mathematical model for predicting the throughput shares of competing cubic and BBR flows. We use this model to show that as more flows on the internet start adopting BBR, BBR's throughput gains are going to diminish. And we extend this observation by modeling it from a game theoretic perspective and show that the internet is most likely heading towards a mixed distribution of cubic and BBR flows. So this is significant from an internet design standpoint because we no longer can design solutions only for loss-based algorithms or only for BBR, but we need to design solutions that work for workloads where you have both flows. Thank you for your time, and I'll be happy to take any questions.